All right, guys. So this is chapter 17, and this is going to be the first chapter in this new branch of physics that we're going to study, which is called thermodynamics. So in this chapter, we're going to talk about temperature, thermal expansion, and ideal gas law. So those are the three main topics of the chapter. So the units are we're going to talk about atomic theory of matter, temperature, and thermometers, which can basically um, sort of like, let's say, an official definition of temperature. We're going to look at more uh, official definition of temperature in the future chapters. Then we're going to look at zeroth law of thermodynamics. So there's a first law, there's a second law, but then it was discovered that there is more fundamental law of thermodynamics. So then they ended up calling that a zeroth law. So we're going to talk about that. Then we're going to see that when the temperature changes, and this is something new that we're going to be looking at when temperature changes, we're going to see that, you know, metal objects can actually expand. So there's a thermal expansion. So we're going to look at in terms of one-dimensional expansion, or maybe let's say three-dimensional, right, expansion, and we're going to look at in terms of thermal stress. Then at the end of the chapter, then we're going to look at um, the gas laws and mainly ideal gas law, where the system we're gonna talk about, let's say, thermodynamic system, where then the system can have what we call specific type of system variables like temperature, pressure, volume, number of molecules, and things like that. And if we talk about this to be an ideal gas, then we can derive an equation which is known as ideal gas law that relates all of those quantities. How the pressure, what happens to the pressure when volume changes, when temperature changes, when number of molecule changes, and all those things. So that can be described with this ideal gas law. So once we derive the equations, we're going to see that there are technically two different ways of representing that equation, at least. We can then learn to solve problems using the ideal gas law. That means, we have a thermodynamic system, let's say container, for example, with certain number of molecules at certain temperature, and then we can change something, like let's say change the volume or change the temperature, thing like that, and see what happens with the system when we change some of those system variables. So those are pretty much in terms of the type of problems we're going to see. All right, so that's basically the main units for this chapter. So then let's look at the let's say the first one, which is atomic theory of matter. So one of the things about thermodynamics is that in this chapter and in the future few chapters, we're going to be studying systems where it's not like uh, one object, or it's not one rigid object or something like that, but it's a system with billions of particles in it. Okay, so we're going to go and look at atomic, sort of like, let's say, at atomic level, sometimes even subatomic level, certain times. But what we're doing here is then we're looking at, for example, if you have a container with water in it, right? So then what we can see here is just basically there's a macroscopic view of that, which is just basically you have a container with some water in it, and there's a microscopic where you can say, okay, so here's a water, and there's, let's say, 200 gram of water, and then in 200 gram of water there are basically a trillions and trillions of water molecules, and then you can look at, okay, so what is each water molecule doing, how is it moving, in which direction, how fast it's moving, and all of those things can be then described. But obviously there are a lot of molecules, there are a lot of atoms, right, in a container. So one of the things we will see is that eventually this type of analysis, right, this type of investigation end up being probabilistic. So that's why most of the time when we look at let's say a little bit higher level thermodynamic studies, that basically becomes very probabilistic. So because uh, we can't really keep track of every single particle, right? And, if it's and you're going to see the number of atoms in a container or in a glass of water, right, is insane. Insane amount of molecules are in just one glass of water. So what we do here is we more or less look at one or two, and then generalize it, and say that on average all of them are basically behaving similar to this, a sample, let's say, molecule size that we chose. Okay, so now one thing we can talk about here is this. So the atomic and molecular masses are measured in unified atomic mass unit. So this U here is basically represents um, atomic mass, right? Okay, or molecular mass. That means if you have just, imagine, right? So if you have a glass of water, so you take one water molecule, so and then you look at, okay, so how heavy it is, because then let's say you have a glass of water, right? You have a glass of water, and let's say it's a 200 gram of water in the glass. But if you know that, let's say if you know the mass of one single water molecule, then you can use that information to figure out how many molecules you have, right? So that's kind of, one of the things we can do. So here you can see, right, this unit, atomic mass unit, right, is defined so that carbon 12 atom has a mass of exactly 12.0000 U. Remember, so all those zeros are actually significant. So then we can say that, 1U is defined as 1.6605 times 10 to the negative 27 kilogram. Okay, so that's basically, so this is the value of one atomic mass. Right, so for example, for water, so we have H2O. So then there are two hydrogen atoms and one oxygen. So generally, for hydrogen, atomic atomic mass unit is roughly 1. So it's actually 1.01 AMU. So let's say you can write it as AMU as just U. So then for the oxygen, it's basically 16 U or AMU. So either way is like correct. So let's write it like this. Now, but we have two hydrogen, right? And if you add them together, so you get basically 18.2 U. This is for the water molecule. Okay, and then we can look at it, right, because of this. This is this carbon, right? Carbon 12. So basically, that's in terms of just one carbon, it has 12 U. But this is just one atom, right? But if you combine atoms together, right, you get a molecule. And in this case, you have two hydrogen with the oxygen. So this is a molecule, altogether 18.02 U. All right, so then we also have this what we call Brownian motion, right? It's basically, you can say it's a jittery motion of tiny flakes in water. These are the results of collision with individual water molecules. And this was also actually interesting enough, was discovered by accident. So, Brownian, it's basically the person name was Brown who discovered this. Is that when you look at water at the atomic level, let's say if you look at water with the microscope, what you see here is the water just literally just water molecules are vibrating a little bit, right? So then they're vibrating, um, and even if there's like you're not doing anything, right? You're not increasing temperature, you're not decreasing temperature, nothing you're doing to let's say your system. There's little of still motion, and let's say actually the Albert Einstein who eventually realized that that's because we're dealing with atoms. So that means those the water molecules, right, at the atomic level, they also have this vibration. So then there's a little vibration, right, there's a little bit of motion, right, and that's what we call now a Brownian motion, which pretty much verified that there is such thing as atomic, like let's say atomic theory, right? It's atomic theory, right? So assume that we're dealing with small object, small, let's say at the lower level, right? Is we have then atoms, and obviously one thing we have here is at that time they thought that atoms is the smallest, let's say, thing we can have in let's say in the universe. So eventually then we discovered that's not the case, right? Atom actually has things inside. There's electrons and protons and neutrons and things like that. So but at this point things like this. So we're never really going to go beyond that. We're never really going to go beyond, let's say, uh, atoms, right? So maybe at some point we will go into like a let's say protons and neutrons and things like that, right? Maybe nucleus. But at this point, the atom is the smallest, let's say, division we can go. So we can have one atom, you combine atoms together, then you get a molecule, right? and so on and so forth. So that's kind of what we're going to be looking at. All right, so you can see, right, on a microscopic scale, the arrangements of molecules in solids, liquids, and gases are quite different. So this actually is important to understand, because one of the things we have here is we have learned about this in physics 37. So there is solid, liquid, and gas, right? Three states of matter. Um, and one thing we can see here is if you think of, like, let's say every object, so let's say a table or a chair or something like, or water, right? Composed of this, atoms or molecules. And when object here is in a solid state, let's say, I don't know, like an ice cube, right? So when water is in a solid state, and by the way, any object, right, any element can be in these three different states. So let's take like water. It could be hydrogen, could be I don't know, helium, potassium, whatever you think. Like anything can be in three states. So let's say water. At this point here is, yeah, water, not an atom. It's molecule, but let's talk about water in solid state, which is ice cube. So you can think like all the molecules are kind of like um, connected together. So this is kind of like seems like string, but it's actually more of like a sort of like a spring type of things that things like this. So that they are connected to one another, sort of like almost a spring like system. So that means thing like this. There's a springs, imaginary, obviously. So like imaginary springs connecting them together. That means they can't really go too far from one another. Springs allows them to move back and forth a little bit, or that means they can vibrate. They can vibrate relative to one another, maybe spin relative to one another and things like that. But they can't really go too far, because then the spring has a kind of like this restoring force, right? It can just pull them back. So that's why the solid, the objects, right, in the solid state can maintain their shape, because the molecules are bound to one another by this sort of like imaginary spring type forces. Now, one of the things we can see here is we can go from a solid state to a liquid state, but that requires certain things that we're going to be learning in the future. But kind of jump ahead, it requires a little bit of energy to be given to those molecules. Imagine those molecules are vibrating, as I mentioned, right? So they're vibrating a little bit relative to one another. If you give them more energy, they can vibrate a little bit more violently. And as they vibrate a little more violently, then they can break away from those spring, sort of like, let's say, forces, or things like this. So whatever it is, a string or a spring, right? They can break away from one another, and then they can kind of move a little bit more freely with respect to one another. So they're not bound to one another by that spring or string forces. But still, there are some, forces keeping them together, so they don't really go too far relative to one another. So that's why, let's say, if you have, empty glass and you pour some water in it, water you know takes the shape of a container, because they can move a little bit more freely relative to one another, but they don't really move too far. So that's why they can take the shape of a container and things like that. But if you give them more energy, that they can go faster and faster and faster, and completely break away for any type of intermolecular forces keeping them together, and then they become basically in the gas state. So the gas state is pretty much the complete random motion, different direction and things like that. And there's also very little forces keeping them together. So in a container, right, where there's the gas, right, so it's much more random than, let's say, a liquid or a solid. So it doesn't take the shape of a container and things like that, right? So and that's, you can see, that's the biggest difference between them. Okay. All right, so we're getting closer to, in terms of like looking at what temperature, because remember, one of the things we're going to see is that when we actually giving them let's say over here, right, so a liquid to solid to a gas, when we give a when we give energy to the system, one of the things we end up seeing is that there is an increase in temperature. Okay, increase in temperature, and that should be a little more obvious, right? Because if they're moving faster, let's say compared to the a solid to a liquid to a gas, so if they're moving faster when they're when you go from solid to liquid, and even faster when they go from liquid to gas, well, that means they can collide with one another with a stronger, let's say, at the higher velocities, right? Or collide with the container wall with the higher velocities. And a lot of times when they collide with one another, those energies then can be converted to heat, and that heat energy then can increase the temperature of a system. So in a way, what we're going to see is that later on, right, there's a very, important, the temperature plays a very important part in all this. But in any case, so what we're going to look at here is this. So if you take some kind of, let's say a solid metal bar or something like that, and measure its length at a room temperature, for example, 20 degrees Celsius, and then increase the temperature, put it maybe in an oven or something like that. So one thing, and then you remove one while it's still really hot and find a way to measure the length again, well, you will see that the temperature will actually, the length will actually be different. It will be longer because the object itself is now at the higher temperature. If you take it and put it in a freezer and wait in a few hours and take it out and measure it again, now you're going to get another, length. This time is less than the one you measured uh, at the room temperature. So what we get here is the object can expand or contract, right? Compress, when there's a change in temperature. And it's a big deal. Let's say if you're a civil engineer building bridges and buildings and things like that, because you have to take that into account. So some material, most of the metal materials, right, expand or contract when there's a change in temperature. Okay, so we can see right now in terms of, like, let's say, what is the temperature? So let's talk about, like, okay, so we're talking about there's a change in temperature and all this, but let's see what is the temperature. Again, this is not, you know, the type of definition that we're going to see of the temperature. We're going to see that more scientific definition of a little bit later on. But think like this. So temperature is related to how much thermal energy is in the system, as I measure, right? As I mentioned already, that in order to go from solid to a liquid, from liquid to a gas, you give your system a little bit of energy. And when you give them energy, then they can move faster or vibrate, more violently and things like that. Well, there's a thermal energy. Well, we can see that is related to the temperature. They're not the same thing, but they are related in a way that you're going to see that there's a direct relationship between temperature and the thermal energy. Okay, but now let's think of it like this. So right now we can define temperature is some kind of coldness or hotness. Okay, so and we can measure it using a thermometer. Okay, and there are different type of thermometers, right? There are thermometers that they use maybe some kind of liquid that can change its shape, or the volume and things like that when there's a decrease in hotness and coldness and things like that. So for example, here we have a glass tube thermometer such as the one right shown in the picture. A small volume of liquid expands or contracts when placed in contact with hot or cold objects. Okay, so you can see, right, if you put it in a let's say in a glass with ice water, right? So you can see, right, thermometer gives you a value of well, I think on the left side is a Celsius, left side is a Fahrenheit, the right side is a Celsius. So what we get here is we can see that it's below zero of the Celsius, and it's maybe like around -5 or -6. Okay, so and that's what we will see for the temperature of water in its solid state when it's ice. Temperature is below 0 degrees Celsius, or roughly, about 30 something degree Fahrenheit. When we have then a glass with the hot water, and then we put the thermometer, then we can see a different reading. And this one reads roughly about, you know, 35, 37 so degrees Celsius and close to 100 degree Fahrenheit. Okay, so in a way, then we can say that, okay, so this is then cold, and then this is hot, because we get different temperature readings, and temperature is a scalar quantity. That means here negative, let's say 6 degrees Celsius, and then here let's say 37 degrees Celsius. Well, this is higher, this is lower, and the negative just means a number. There's not no direction, nothing like that, right? That's what the scalar quantity is. So it just means that even if I had, like, let's say negative 37 degrees and compare it to positive 37 degrees, well, they're not the same different direction. 37 is much higher temperature than negative 37. That means you have to understand, right, what, when we're dealing with a scalar here. All right, so again, there are different type of thermometers, right? We can, there are some thermometers that have resistors inside, and some thermometers that use, mercury and all of those things. The idea here is that it reacts to the small change in temperatures in such a way that it's measurable for us in a room, in our environment. Okay, so there are objects that basically barely, let's say, change their shape or size when you go from negative, let's say -6 to 37. So if you have like, let's say aluminum barely changes, when you go from -6 to 37. But let's say mercury does change quite a lot, and we can see that, and put it in a thermometer and use it to measure things. All right, so again, so common thermometers used today include the liquid in glass type and the bimetallic strip. So this is another way of looking at it. So we can again use this thermometers just to measure the difference between, let's say, two different conditions. When is it cold? When is it hot? Right? But technically, it doesn't really tell us much else except that one is hot, the other one is cold. Okay. So here's a scale that on left side is Celsius, on the right side is Fahrenheit. So this is mainly so that you can see some of the important points on the scale. And again, this scale is a human-made scale, right? Celsius is, basically designed by a guy named Celsius. Fahrenheit is by a guy named Fahrenheit. And each one more or less take water as a reference. So the Celsius take 0 degrees to be the freezing point of water, which is equivalent to 32 degrees Fahrenheit. And then 100 degree is a boiling point of water, which is roughly 212 Fahrenheit. That means Celsius, so sometimes is known as a centigrade, because he takes those two critical points, right? Two important points for water, boiling and freezing, and breaks it down into 100 equal parts, just like a centimeters, right? Relative to a meter. Okay, so, and obviously those points are important because let's say what you have here is, if you talk about, let's say, again, Celsius has a scale relative to water. That means here you have water in solid form, and then 0 represents, when it changes the phase, changes the state. It goes from solid to liquid. That's why it's called a freezing or a melting point of water, right? So you can go from solid to liquid or liquid to gas, and it always happens at that 0 degree temperature. 100, then it goes from liquid to gas. That means anywhere above 100 degree, water is in gas form. Anywhere below 100 degree, it is basically in liquid form. So that's why that's what we have here is a liquid, solid, liquid, and gas. And those temperatures are important because that's where you have your change of phase. Also, we have a Fahrenheit. Let's say the question is that how come Fahrenheit doesn't have 0 for the boiling, the freezing of water? Well, I think the Fahrenheit uses the dry ice as a reference rather than liquid ice, let's say. So he uses dry ice, so his 0 is a little bit different. All right, so this slide basically gives you some of those, let's say, conversion between one, let's say, scale to another scale. So you have Celsius, you have Fahrenheit, and then you can see, right? So here's the equation going from, let's say, Celsius. If you're giving Celsius, go to Fahrenheit, and from here you can then rearrange and go to the, Celsius. If you're given Fahrenheit, so this will be 5/9 temperature in Fahrenheit minus 32. So this will be then the temperature for the, temperature conversion equation for that. All right, so now we also have this different type of scale, which is known as a Kelvin scale, Kelvin temperature scale. This is completely different. This is probably it came at the later time, designed by a guy named Lord Kelvin. So that's why, the name is Kelvin scale. What he did was to not use any type of element or molecule as a reference. So his temperature scale actually represents, let's say, the 0 of basically of the Kelvin scale represents, in a way, what we call absolute 0 temperature. That means, 0 degrees Celsius is where water melts or freezes. But for example, hydrogen doesn't do that at that temperature. Aluminum doesn't do that at that temperature. Helium doesn't do that at the temperature. So, but when you have 0 of the Kelvin scale, well, that is known as, again, absolute 0, because at that temperature, every single element or atom or a molecule in the universe pretty much stopped moving. Okay, so I'm gonna talk about that a little bit later on, but the idea here is this. Here's the temperature scale for the or the conversion, sorry, for the Kelvin. That means, for example, to go from Celsius to Kelvin, you take the temperature in Celsius and add 273, or other way around, take the temperature in Celsius and then say temperature in Kelvin minus 273, which means, for example, if the temperature of Kelvin is 0, that means 0 Kelvin is when the temperature of the Celsius is negative 273.15 actually degree Celsius. Okay, so I'm going to talk about that because I want to later mention like why and how Kelvin came up with his scale, and there's a really nice history behind that. So there's a few slides when I can go over that. But at this point, think like this: there are three scales, three temperature measuring scales: Celsius, Kelvin, and Fahrenheit. I almost never use Fahrenheit. Okay, so, well, in this class, what I mean. So, and mostly it's going to be Celsius or Kelvin. The idea here is that I can use both either Celsius or Kelvin, because one important thing about Celsius and Kelvin is this. When you look at how the temperature changes, that means, let's say you go from initial temperature to final temperature. So for the change in temperature in Celsius actually corresponds to exactly same temperature change in Kelvin. That means delta T is exactly same for the Kelvin and Celsius. Well, that's not the same for the Fahrenheit. That means I cannot say that this is also equals change in temperature in Fahrenheit. That will be, false. But change in temperature, delta T in Kelvin and Celsius is exactly the same. So that's why every time in an equation there's a delta T, I can use either Celsius or Kelvin because they are the same, right? Delta T's. But every time in the equation, just a T, you have to use Kelvin rather than Celsius. All right. So here's another example of a thermometer, right? You can see it's a constant volume gas thermometer, depends only on the properties of ideal gas, which do not change over a wide variety of temperatures. Therefore, it is used to calibrate the thermometers based on other materials. So in a way, so this uses some of those fluid dynamics that we learned, right? So you can look at it in terms of, measure the temp, like let's say pressure this height, and then you have that same pressure over here because of that horizontal reference mark, right? And then use that pressure, at this point, and then use that to later on measure, let's say, for example, a temperature and things like that, because we will see that there's a relationship between pressure and a temperature when we get to the later parts of this chapter. All right, so then let's look at this zeroth law of thermodynamics. As I mentioned, the zeroth law of thermodynamics is something that was discovered after there was first law and second law of thermodynamics. So the first law of thermodynamics, in a way, it's a conservation of energy. Okay. Second law has actually different ways of describing, so we're going to look at it later on as well. But in a way, what we have is this: the zeroth law of thermodynamics gives us condition of what we call thermal equilibrium. Okay, so this is the law for pretty much thermal equilibrium. Okay, thermal equilibrium, you can think of it as this: if you have two objects at different temperatures, if you put them together in contact in the same system, right, then there's going to be energy exchange between them. So energy exchange then will change the original temperature of those objects. So think like this. So the idea here is that, so let's say you have object A and you have object B. Okay. Now, if you have a temperature A and then temperature of B, and put I for the initial. So, and let's say they're different, right? So let's say, temperature of B is higher than temperature of A. So then what happens here is that as you put them together, there's going to be then heat exchange. Okay. And energy, this is a new type of energy, just, thermal energy, will always go from, even if those objects are not moving, but because they have a different temperature, the energy will flow from hot to cold. We'll see that's basically what the first law of thermodynamics in a way tells us, in which direction it is pretty much moving. So it always goes from hot to cold. And again, because let's say B is hotter than A, then we can more or less assume so there's going to be a transfer of energy going from B to A, hot to cold, until eventually, that means, the temperature of B will decrease, temperature of A will increase, until eventually temperature of A and temperature of B, final temperatures, are exactly the same. Then we can say that they reached thermal equilibrium. Okay, they reached thermal equilibrium. Now, for example, after this, after waiting that A and B in thermal equilibrium, let's say I move this B here. So I move the B here, and let's say I made it contact, basically be in contact with another one. Let's say box C. Now, if I see that temperature of B and temperature of C are, that means things like this. That means there's no heat transfer between them. That means there's no heat transfer between B and C. I put them together. There's no heat transfer between B and C. Then I can conclude that temperature of B and C are exactly the same. And if the temperature of B and C is exactly the same, then I can conclude that temperature of A is same as temperature of C. Because when A is in contact with B, there is no heat transfer. When B is in contact with C, there is no heat transfer. That means C and A are also have the same temperature. So that's kind of what it says, right? So zero law thermodynamics says that if two objects are each in equilibrium with a third object, they're also in thermal equilibrium with one another. That means if I put A and C together, right? So if I put A and C together, there's going to be no heat transfer between them. Okay, so that's pretty much a zero law of thermodynamics. All right. Now, temperature can be thought of as the property that determines whether an object is in thermal equilibrium with one another. Okay, so that means we can also use that, right? You put object, put a thermometer on top of it, measure 22 degrees Celsius. Have a second one, put on top of it. If it's also 22 degrees Celsius, that means you can put them together and assume that there will be no thermal energy moving from one to another because they are in thermal equilibrium. Okay, so two objects in thermal equilibrium with each other are at the same temperature. Okay. If two objects have different temperatures, they are not in thermal equilibrium with each other. Kind of continuation of the zeroth law. That's why when you put ice cube in water, in like let's say a glass of water, well, the temperature of water is higher than the temperature of the ice cube. So there's a heat exchange between them. Heat goes from hotter, which is water, right, to a colder, which is ice cube. So that means liquid water loses its energy. Ice cube gains its energy. Well, an ice cube gains its energy, its temperature increases. As the water loses its energy, its temperature decreases. That's why, eventually then, when you drink that water, right, it's nice and cool, right? Because you put the ice cube over there, and what you're doing, you're just basically removing, right, the energy from water, and that energy removal from water makes its temperature to go down. So that's why then you have iced tea or something like that with ice so that you drink something nice and cool. All right, so, okay, so coming back to this thermal expansion. So remember, so as I said, right, if you have a metal bar, then let's say at some room temperature, you measure the length. Let's call this L naught. Okay. And then if you increase the temperature, some higher temperature T, you measure the length of the bar again, well, what we'll see is that it's a higher, longer length, right? If the, let's say, T is greater than T naught, what we will see is that there's a delta L amount of change in length of the bar. Okay. So then what we can do here is we can then calculate, right? So this, L, well, so technically this should be delta L. Okay. So delta L is equals to L naught times 1 plus alpha times delta T, because this represents change in change in length. So change in length equals original length times 1 plus alpha times delta T. Well, this delta T is the change in temperature between those two. Alpha then is known as a coefficient of linear expansion. Okay, coefficient of linear expansion. That means what it will do here, it will tell us then by how much, let's say, this type of material, right, can change when there's a change in temperature. So alpha is very specific to the material, because like aluminum, changes length differently if there's a 10 degrees Celsius, increase in temperature. But how much, let's say, aluminum will change for that 10 degrees Celsius temperature difference will be different than when by how much the copper will change. Okay, and this alpha more or less represents that. So it's kind of very specific to the material constant. Yeah. So this is something that you're going to be given unless it asks you to find it. But that's kind of let's say if you look at it here, coefficient of linear expansion is right here. So you can see, right, you have the aluminum, brass, copper, they all have different, values for the coefficient of linear expansion. And mostly you can see, right, it's for the more or less, a solid material. So when you go to liquid and a gas, you don't see any, linear expansion because we assume that this is more of like, let's say, a solid object kind of thing. But then we can have what we call a volume expansion, which can actually happen to the solid, liquid, or a gas. So both water, or or let's say, or hydrogen, right? When it's in a gas form, right? They all can expand if you are looking at sort of like a three-dimensional expansion. Okay, so that's what we have over here. There's also a volume expansion, which is similar, except that it's relevant to liquid and gases as well. So then this is the change in volume. So let's say you have, I don't know, like here's a container. This is your original volume and at the room temperature. And then as we increase the temperature, this, I don't know, balloon or something like it, right? So it can actually expand. So then this is basically your final volume. Then what you want to do, look at the change in volume between those two, right? So this is V final minus V initial. And that is equals to a beta, which is then the coefficient of volume expansion times original volume times delta T. Okay, so one thing we have is that this beta is about 3 times alpha. Why is it 3 times alpha? Because remember, volume, right, is sort of like let's say three-dimensional expansion, where the alpha is a one-dimensional expansion. And going from, let's say length to a volume, volume is basically length times length times length, right? So 3 equivalent of lengths change. So that's why it's 3 times alpha. There's also actually, delta A, which is the area. So this is then equals to gamma times original area times delta T. And then gamma is equals to 2 times alpha for any material. So you can also have, something like this. All right, again, refer to this table for the values of the linear expansion or the volume expansion. Okay. All right, so let's look at an example here. So the length of steel beam increases by 0.73 millimeters when its temperature is raised from 22 degrees Celsius to 35 degrees Celsius. What is the length of the beam at 22 degrees Celsius? All right, so here what we can do is we can see that this information is the change in length, right? So it increases by that much. That means it's 0.73 millimeters or times 10 to the negative 3 meters. That's our change in length. This is our initial temperature, which is 22 degrees Celsius. This is our final temperature, which is 35 degrees Celsius. And we're given steel beam. So we go back to the table. Let's see, there you go. So, and find steel beam right here, iron or steel. So 12 times 10 to the negative 6. That means I can come back and can say this is then alpha is equals to 12 times 10 to the negative 6. Okay. Also look at the units, right? Per degree Celsius or per Kelvin. So technically, because it's delta T. So it can be, either way. So 12 times 10 to the negative 6 Celsius to the negative 1. Okay. Now, what I have is then delta L is equals to L naught, let's say, right? Then 1 plus alpha times delta T. Okay. And this particular example, I want the original length of the beam at 22 degrees Celsius. Okay. That means what I have here is, let's say this was the original beam. And now because I increase the temperature, there's a little bit of increase, right? And this delta L represents that increase. So rearrange this. I can, divide both sides by 1 plus alpha times delta T. Then I have delta L over 1 plus alpha times delta T. So then this will be in terms of delta L. which is 0.73 times 10 to the negative 3 meters, divided by 1 plus 12 times 10 to the negative 6 degrees Celsius, and times delta T. So delta T will be final, 35 degrees Celsius minus initial, 22 degrees Celsius. So then I can calculate this and find basically original length, which should give me 4.7 meters. Okay. Here's one more example. So a copper cylinder is initially at 20 degrees Celsius. At what temperature will its volume be 0.15% larger than it is at 20 degrees Celsius? All right. So that means we are dealing with another example of expansion, right? But this is a volume expansion because we're looking about, talking about the volume. That means we are using this delta V equals V naught times beta times delta T. Okay. Again, because this is copper, I can get the beta from the table. Well, this is then 5.1 times 10 to the negative 5 per Celsius, degrees Celsius. Okay. Now, what I have here is this. It says 0.15% larger, which means then if I look at, see, if I divide this both sides by this, right? Then what I have, this is then delta V over V naught. It just basically means that 0.15%, basically divided by 100 to get the decimal of that. So that means delta V over V naught is equals to 0.150 times 10 to the negative 2. Okay. That's basically the decrease, right? Then, and I want basically at what temperature, right, it happens. Well, I know that delta V over V naught is equals to this, and according to the equation above, this is equals to beta times delta T. Okay. That means just rearrange, divide both sides by beta, then I can calculate delta T. That means delta T is equals to 0.15 times 10 to the negative 2 divided by 5.1 times 10 to the negative 5 per degree Celsius. And I can calculate delta T to be 29.4 degrees Celsius. That means that's my temperature difference. Okay. But I know that delta T here is T final minus T initial equals 29.4 degrees Celsius. But my T initial was 20 degrees Celsius. That means final here is 29.4 degrees Celsius, then plus 20 degrees Celsius. So 49.4 degrees Celsius. That means only at this temperature, right? Then I will have then the volume increase by 0.15%. All right.